That's good. So let's just, really zoom out a lot to the beginning of this lecture and just recap all of the different machine learning types and models we have learned. So in the beginning, we learned, or someone in the beginning, we learned about classification with deep neural networks, and we learned that this is a technique where you take some data. That data is belongs to a certain type of classes, and the task is that with the neural network, you identify the different classes in the data. So here, for example, you have different digits, and you want to know, is this a digit 2 or is this a digit 4? And the neural network is able to detect this for you. So this is a supervised learning task, and it is usually non-probabilistic. You can make it probabilistic with some caveats though. Then another application of machine learning is regression tasks. Here we are interested in getting some continuous parameters from our input data. And generally, again, this is a supervised learning task. So we need to have a labeled data set where we have, for this training data set, we have the true answers, and we can match the two, and we can teach the neural network to match the two and then give us the parameters for data it has never seen before. So far, clear? So yesterday, we touched upon a new machine learning, or new branch of machine learning, which is called deep generative models. And deep generative models are unsupervised. And what they all have in common is that they are able to learn, or they learn the probability distribution of the input data. So there's no labels here, just the input data. Every input data follows some probability distribution. And these models somehow, there are different techniques, lots of different techniques to do this, but they somehow learn this probability distribution. And then they give you a possibility, they give you a tool to sample from this probability distribution. And this means you can generate new data, okay? So this is shown here, the training data here, and we have data generation. These are fake images that the model found for us. Now, some of these models can only generate. They can't do anything else. For example, GANs are adversarial neural networks. But a lot of them can do another thing. They actually can evaluate the density of each of these data points. And so these models are, as I said, unsupervised, and they are fully probabilistic by design. That's how they've been built. And that's kind of what I tried to show you yesterday. Everything all right? With this derivation that we did, just to, those are usually there's quite a bit of math behind these models. But the nice thing about them is that they're fully probabilistic. So yesterday, we learned about one of these models, one of the most famous ones, which is the variational autoencoder. And we saw that the variational autoencoder is a generalization of the autoencoder, where the encoder network is now replaced by a posterior. So instead of mapping our input data X to a single point in the latent space, it gets mapped onto a distribution, the posterior distribution in latent space. And then on the other side, the decoder, again, a latent space is, point Z is not just matched to a single reconstruction point, but we have the likelihood here, and the likelihood is a probability distribution over possible reconstructions. So the VAE does also performs a density estimation. This is the training objective of the VAE, is to maximize the probability of the data under the model. And it does this in an approximate way. And this is the formula we derived yesterday. We call it the evidence lower bound. So the evidence lower bound solves the marginalization on the right-hand side here over the latent space approximately with a variational approach, where variational means that we have an approximate posterior Q, and the approximate posterior Q is varied to best fit the actual posterior, which is an intractable posterior. So it has free variables phi, and we find by fitting this model, we find the best parameters phi to satisfy this equation. And the elbow we saw has two parts. The first one is an average over the likelihood, which is basically minimizing the reconstruction error, just like in the autoencoder. And then it has a second term, which is a regularization term. And we saw that this is the Kullback-Leibler divergence or distance between the approximate posterior and the prior. And we chose the prior to be a Gaussian prior. And what this term does is it enforces that the average latent space distribution is a Gaussian distribution. And I've shown this here by, painting this distribution as a round blob. And this is different to what we saw yesterday morning in the autoencoder, where the latent space distribution can be very blobby and disconnected even. And this is the disconnected latent space distribution can be good for some things, like, for example, clustering. But if we are interested in things like data generation or data interpolation, then we want a continuous latent space. And that's why we need this regularization term in the autoencoder, in the variation autoencoder. Questions so far? Okay, I hope this helps bringing yesterday's lecture a little bit more into perspective. Let's talk a little bit about the applications of the variation autoencoder. So the first application is data interpolation. So what we can do is we can take real data points. They're on the extreme ends here on the right, so the real photos, and we can map them into the latent space, and then we can connect the two in the latent space, for example, with a straight line. And because the latent space is continuous, every point along this line will result in a sensible image once we pass it through the decoder network and bring it back into data space. And so we get these really, really nice smooth transitions between very different phases, for example, here. And that the same would be true for other data sets. Very similar to this is the data generation. So because the average latent space distribution is Gaussian, we can sample from this Gaussian, which is the prior, and then take these samples from the prior and pass them through the decoder. And this will give us images that are realistic. That wouldn't be the case for an autoencoder, because again, an autoencoder, we don't know what the latent space distribution looks like. I mean, we could try to fit it, but without fitting it, if we just sampled from a Gaussian, then we would take samples from areas in the latent space that the decoder has never seen before, that the decoder has not been trained on, and we would get nonsense here on the right-hand side. But with the variational autoencoder, we actually get sensible images. Okay, I see people nodding, that's a good sign. Right, so now moving on to a little bit more involved applications. So one application which is really interesting for science, and this was touched already in the autoencoder lecture, is anomaly detection. So the obvious thing for autoencoders is to use the reconstruction error. And here the assumption is that if you have a bad reconstruction error, that means the model hasn't seen similar data before. It has a hard time reconstructing this data. So probably it is an anomaly or an outlier. So you label high reconstruction errors as outliers. This works in some applications, but it has some problems. So what I'm showing here is a model that has been trained on a data set that's called fashion MNIST. So this is clothing, different kinds of clothing. And when we give it as input digits, then if we use a small latent space dimensionality, I think I used 4 here, then you can see that the reconstructions are really bad. Okay, it actually reconstructs clothing. But as we increase the latent space dimensionality of this model, it actually becomes more and more expressive. And the same would also be true if we had a more and more powerful decoder, like a deeper decoder that has more free parameters. And then it's actually starting to be able to recover these points. So in some cases, and in certain settings, we can get a low reconstruction error, even though we are looking at anomalous data. So the generative models with their density estimation give us another path or another method to detect anomalies. And that is to use the density estimation itself. So here, the idea is that we just look at the density or the value of the probability of each data point, and those with a low probability we say are anomalous. And that seems to be, I mean, when I first heard about this, I was like, oh yeah, that's so obvious. That's like a really good idea. But actually there's a lot of literature in the machine learning community that finds that this usually doesn't work. And that is extremely frustrating. And it's still an open question and a question that is being investigated. So I'm quoting some of the literature up here if you're interested. But basically what can happen is that if you train a neural network, here again, on this fashion MNIST data set with the clothing, and you evaluate the probability of the same data set or the test data set of this data set under this model, then you get lower probability in some cases than when you show them outliers or when you show it outliers. So the outliers actually get a higher probability under this model. And that's of course extremely problematic and is catastrophic failure. And so that's something to keep in mind. Sometimes it works, sometimes it doesn't, and you really want to make sure that you test your model and make sure that you have one that is working. Let's talk about another application that is working, and that is also very relevant for science. So when we take measurements, usually they're imperfect, right? I mean, we usually have some kind of mask in our data, shown here on the left. We have noise in the data and mask. This is the middle panel. And sometimes we have an image blurring, some kind of kernel that our image is convolved with. And usually we kind of know the properties of these things. We know the noise level, we know the mask, we kind of know the kernel, or roughly know the kernel that our image was convolved with. So one of the tasks that we often have is to reconstruct this data and find the most likely underlying image given this corrupted input image. So in probabilistic terms, what we are interested in is the probability of the uncorrupted image X under the corrupted image Y. And through Bayes' theorem, we can relate this to the probability of Y given X. That should not be an equal sign, that there's a normalization missing, but otherwise it's correct. So you have the likelihood here on the right-hand side and the prior. And this has two problems. The first problem is that X and Y are both very high dimensional. And working with probability distributions in high dimensions is extremely hard. Usually, I mean, there are sampling algorithms, but usually when we are at the dimensions of images where we are looking at 100 times 100 pixels at least, it gets unreliable to sample these probability distributions. The other problem that we have is that we need the prior P of X, the probability of the uncorrupted data. And we usually have no way of expressing this. So traditionally what people use here are just Gaussian priors, which kind of means that your image is in a way smooth, and then you put some smoothness scale on that image, or they use an L1 prior, which is kind of like a sparseness prior that is put on this. But none of them are really like 100% physically motivated, or they actually don't encode the full knowledge that we have of the underlying image. So with VAES or with generative models, we can go around this, or we can solve this problem. I haven't mentioned here on the left-hand side, this is our forward model, right? So the corrupted data, the observed data is the uncorrupted data with some corruption operator applied. So the corruption operator would be the mask, for example, or the convolution. And then we have also additional noise. And the assumption is that we know both the corruption operator and the noise level. So now what we can do with VAES, for example, if we have access to uncorrupted data, This is like the easiest way to do it. Of course, there's ways to do it if you don't have access to it, but let's say we have access through some maybe a data set where the exposure was longer, so the noise is lower. So we have that data set. What we can do is we can train a variation autoencoder on it. And then with this, we can, in this forward model, replace the uncorrupted data with its generative process. So we can technically bring this problem into a lower dimensional space, the latent space Z. So instead of working in hundreds or thousands of dimensions, we are now working in tens of dimensions, typically. And the other thing we're getting with this is that we now know the exact prior, because we have trained the variation autoencoder such that the prior is Gaussian. So the Gaussian distribution is the correct prior for this problem. So instead of writing this problem in X space as we did before, we now write it in Z space. And in Z space, we are operating in a lower dimensional space where we can actually use maximization, optimization algorithms to find the maximum of this, or take samples from this distribution. Questions? How I choose the corruption operator. So usually the corruption operator is known. For example, if you take some data, you usually know what you have masked, right? There's like, was a bright star that you masked. So the corruption operator would be a matrix of zeros and ones, where zeros is for all the pixels that are masked. Okay, so let's look at some examples. So here on the left-hand side, we saw these corrupted data points. Usually I let people guess what the underlying digit was. This time I didn't do it, but I think you can kind of tell. So the underlying image here on the left row was a 2. This is the lowest image is the 2 that was underlying. And above that is the reconstruction that I'm getting. So here what I've done is I've looked for the maximum of P of Z given X, which was, which we said, looked here, this was this thing. So I just maximized this with respect to Z. So I found the most likely Z, and then I forward modeled it into data space. And the same here, so the noisy and masked one is the 4. Obviously, it doesn't reconstruct things that are a little bit unusual in the data. So this 4 here has this little wiggle on the bottom, and this doesn't get reconstructed because there's nothing in the image that hints towards there being this little wiggle, okay? And the same applies to the 9 here. So the 9 had this little bit of a sharp edge on the upper right corner, and in the reconstruction, we don't see that. So that's kind of the shortcoming of only looking at the maximum of the distribution. What we really want to know is what are all of the possible digits that are compatible with this corrupted image. So we want to do some kind of uncertainty analysis, some kind of posterior analysis. And this is shown here on the right, where so the input image here is heavily masked, meaning that it could be anything. It could be a 9, it could be a 4. The model doesn't know. So the posterior for this is actually bimodal. It has two maxima. One maximum or one region of high probability is associated with 4s, and another region of high probability is associated with 9s. And because this is low dimensional, we can actually sample this distribution, and then we can get, we can look at all of these samples in data space, and we can see, you know, what is the range of data that is compatible with this observation. Questions? Is that clear so far? Okay, cool. So these are all of the cool applications of VAES, but also more generally generative models. Now, I already hinted with the anomaly detection at the fact that things don't always work great. So VAES actually, and that was something that I was hoping we could look at in the exercises yesterday, but then we didn't have enough time. So I just want to go through it here. So VAES actually have a couple of problems. So one of the problems that VAES usually have is that even after training, the average encoded distribution or the prior is not perfectly Gaussian. And that's usually because the model has a really easy time getting a really good reconstruction error. So it keeps minimizing the reconstruction error and doesn't focus too much on this regularization term. So that means that, for example, our samples won't look great because we will still be sampling from regions that were not covered in the training. Another one is that our approximate posterior distribution, the Q, is actually often not a good approximation to the true posterior. And that's hopefully something we will see today in the exercises, where you can sample from the true posterior, but then you can also evaluate the approximate posterior, and hopefully you will see that they don't necessarily match. So even though I think it's still okay to use this for training the VAE, the Q posterior, you should not try to use the Q posterior for science, because it is simply not a good approximation. And then another thing is that because we have this imbalance between the two terms in the elbow, there's often a lot of hyperparameters in the training that you have to optimize to get really good results. So for example, how many samples do I draw from Q every time I evaluate my elbow? What kind of noise level do I set in my Gaussian likelihood? All of this will have an influence on the balance between the two terms and will lead to different outcomes. And all of these problems are well known, and because of this, there's actually a lot of literature on how to improve VAEs. It's like almost too much for a beginner. One of them that I want to point out that I think is probably one of the most common ones and easy ones is a beta VAE, where we use just the scalar parameter beta during the training to either upweight or downweight the regularization in the KL term in the elbow. Questions about these problems? I'm planning to walk through yesterday's exercises after this, so we can also see examples of this failure a little bit more. Okay, so we've spent a lot of time talking about VAEs, so I think it's time to talk about another generative model. So as another example of a generative model that I find pretty exciting, I want to talk about normalizing flows. So yesterday, or maybe, yeah, I think it was yesterday, someone asked in the autoencoder session whether it would make sense to have a decoder that is the exact inverse of the encoder. And this is what normalizing flows are. So normalizing flows, they don't have any compression, because the moment you have compression, you can't have an inverse, right? You're not bijective anymore. So they preserve the dimensionality of the data. And it's just a single transformation. And this transformation has an exact inverse. And this transformation brings us from the data space to our latent space, and then back vice versa. So you can already by the fact that it has to be bijective, kind of limits the type of architectures we can use here. But the nice thing about the bijectivity is that the bijectivity gives us a way to relate the distribution on the right-hand side, which is the latent distribution, which is the one that we choose. So again, we usually choose a Gaussian here, with the actual data distribution. And that's just conservation of probability mass. So we're just doing a change of variable from space X to space Z, and a change of variables. If we want to conserve the mass, so we want to conserve the normalization of our probability distribution, which is 1, means that in addition to our probability, we are getting the Jacobian of the transformation. So that's just really simple calculus 1 change of variable formula, basically, that goes in here. And this is also the shortcoming, or the caveat in these models, or what limits these models, is the fact that we have to evaluate this, we have to evaluate this Jacobian. And a Jacobian can be, a high dimensional matrix, and can be very expensive to to evaluate. Actually, so this is the determinant of the Jacobian, and then I take the logarithm here in case you're confused about the notation. So this evaluating this is usually expensive. So normalizing flows have architectures that make this Jacobian determinant easy to evaluate. So one of the examples, for example, is real NVPs. Real NVPs. In real NVPs, in the transformation, we have several transformation layers. And in each layer, we only transform half of the variables. And this leads to a triangular matrix. And for a triangular matrix, the determinant is just given by a diagonal. So that makes this determined evaluation very easy. But at the same time, it limits the space of transformations that we can explore with this model. To give you an example, what does this look like in 2D? So a data space distribution like this, that is a spiral. All of these models up there that I mentioned up there can definitely transform this into a Gaussian, and vice versa. If you sample from this and pass it through this network, it will give you the spiral. So I think this is super impressive. Are there questions about this? I know this is a lot, and I'm doing this a little bit more superficially. You don't have to know the details. I just want you to know that there are bijective models that also estimate the density, and they estimate the density directly. There's no approximation here. Remember, in the VAE, we had the elbow, which was a lower bound, but this is actually an actual model for the density itself. No questions? Okay, cool. How am I doing on time? Oh, not too bad. Okay. So this actually is already, I think I'm already at the end here. I just want to say a couple of words about today's exercise. So in today's exercise, the idea is that we're going to use a normalizing flow to improve our VAE. So we said before that with the VAE, the problem is that the prior is usually not Gaussian. But now we just learned about a model that helps us transform an arbitrary distribution into a Gaussian. And so we're going to add, instead of a Gaussian prior, we're going to add a normalizing flow prior to the VAE. This is going to make it easier for the VAE to get a Gaussian prior distribution. And therefore, it's going to be easier for the VAE to minimize both terms, the reconstruction error and the regularization term, at the same time. Then I have another exercise, but again, if you only can solve one of them, that's fine. We don't have to go through all of them, where I'm trying to show you that Q of Z is usually a bad approximation to the actual posterior. So where we're going to sample from both and compare the samples of the two. And then the last one is to reconstruct corrupted data by maximizing the posterior. This was the example with the blurry digits that we looked at, but this is going to be on real data again, the SDSS data set, where you will find the maximum of the posterior to reconstruct the unnoised and unmasked spectra from masked and noisy spectra. Questions? If not, I think I can finish here.